Hello students. So today we will see the NCERT chapter 3, classification of elements and periodicity in properties, in which we will see section 3.5. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. Our objective would be today to understand the significance of atomic number and electronic configuration as the basis of periodic classification. In this, we will see the NCERT section 3.5, electronic configuration of elements and the periodic table. And we will do a related problem to it, which is problem 3.2. So first, let us understand that what is groups and periods. So we have already dealt about it in the previous class. Now we will look on the important points that we have seen yesterday. First is, what are groups? So groups are vertical column, whereas periods are horizontal rows. Now there are 18 groups in total, whereas there are 7 periods in a periodic table. If I talk about the significance of groups, then the elements that are present in the same group will have the similar outer electronic configuration. Whereas if I talk about the significance of period, then in that case, the highest principal number of the electronic configuration of the element simply defines the period number. Example, if I take for the similar outer electronic configuration in case of groups, so you can take the example of lithium, sodium and potassium. They fall in the same groups and they have similar outer electronic configuration, which is S1. Now, if I talk about the period, then suppose we take the period number 2, carbon and nitrogen. Now, if you look at their highest principal quantum number in their electronic configuration, so we have written the valence one, you can see that it is 2. So therefore, both of this carbon and nitrogen will belong to the period number 2. So if the element is falling in the same group, then they will have similar chemical properties like the lithium, sodium and potassium. This is not followed in the case of period, so the properties do change if we move from left to right across a period. Then moving on to the number of elements, so there is no such defined number for the case of groups. For the case of periods, it is there. So the first one has 2 elements, the second and third have 8 elements, fourth and fifth have 18th, and sixth and seventh have 32. So remember, this is very important to be remembered. Questions are asked from here. Then what is the IUPAC numbering? It is 1, 2, 3, 4 till 18, and for the period it is 1, 2, 3, 4, 5, 6, 7. Now this group number is being replaced from the previous traditional numbering, which is according to the Mendeleev, that is 1A, 2A. So that has been replaced, but I would suggest you to keep in mind that numbering also, because it is important. Questions are asked using those notations also. We have seen that in the previous class. Now we will look on each period one by one and try to understand that how this electronic configuration goes on or changes for different periods. The most important line in that discussion would be that the number of element in each period is twice the number of atomic orbitals which are being filled in that period. Let us take the example of first period. We know that for the first period, the highest principal quantum number should be 1, and 1 consists of only one orbital or one subshell, which is 1s. And 1s has maximum of 2 electrons, we know it. Therefore, your first period will have only 2 elements. What are those? The first one is hydrogen, which has an atomic number of 1. Therefore, its electronic configuration is 1s1. Then we have helium, whose atomic number is 2, and its electronic configuration is 1s2. Again, remember this point, since it is the first period, therefore the maximum allowed principal quantum number will be 1, and hence the only subshell which is possible is 1s, and the only orbital which is possible is also 1s. And since 1s has a maximum of 2 electrons, therefore the first period contains 2 elements. Now moving on to the period number 2. How do we see the electronic configuration of period number 2? If I talk about the second period, then it is associated with the second energy shell. Again, since your principal quantum number, highest which is possible, is 2 in case of second period, therefore we can have 2 orbitals. Okay, we have 2 subshells, not orbitals, we have 2 subshells, which is 2s and 2p, related to the second shell. Now this 2s and 2p subshell will have a total of how many orbitals? 4 orbitals, 3 of p and 1 of s. So in 2s subshell there will be 1 orbital, and in 2p subshell there will be 3 orbitals. Therefore the total number of maximum allowed electron is 8, and hence your second period contain 8 elements. So this is the reason behind your numbering, or you would say the number of elements in the periodic table. Now questions are asked from this part. Try to remember this part. You will easily score marks both in your competitive exam and in your board exams also, because every year questions are there from the electronic configuration, and it is very easy to remember those. So here is a table for you. So we have of lithium. You can see here that slowly your 2s orbital is filled first from lithium to beryllium. So it is 2s1, 2s2. Then from boron to neon, you can see that the p orbital is filled successively. 1, 2, 3, 4, 5, 6. Now here is an important point for you, and this is true for the first period also, that you have not noted any anomaly in it. Means the electronic configuration is going in accordance with the above principle. There is no exception. Till neon, we are sure about it that there are no exceptions. Okay, moving on to the next one. Now in this you have various elements, remember those. So the neon is called as the noble gas. So if I ask you what is the noble gas here, it is neon. What is the halogen that is present here in this table? So it would be fluorine. What is the alkali earth metal present in this table? It is lithium, and the alkaline earth metal is beryllium. We will talk more detail about these subdivisions related to the S, P, D and F block, but for now you should remember that what are halogens, what are noble gases, what are alkali earth metals, and what are alkaline earth metals. Again, if you see that it is S1, just remember this, that if it is S1, it will be a alkali earth metal. If it is a S2, it is alkaline earth metal. If it is S2P5, that is 7, then it will be a halogen. And last, if the octet is complete, then it will be a noble gas. Why do we call it a noble gas? Because it is not reactive. Now moving on to the next period. Now the third period is very much similar to the second period, as it has the same number of same number of elements. But why is it so? When we move on to the third shell, the number of subshells possible for the third shell increases. We know it. It has 3s, 3p and 3d, but still it has the same number of elements in the period 3. We will look how this is possible. So whenever we talk about the third period, it has 3s, 3p and 3d. But the problem is that before moving on to the 3d, we have to fill the 4s. Now the question arises, why? Why are we doing so? Why are we not filling the 3d first and not doing the 4s filling first? What is the reason behind it? So my question is that, why are we filling the 4s first and not the 3d? Yes, it is according to the above principle. Your 4s has a lower energy than the 3d. As a result, you will first feel the 4s. And that is the reason in this period we have only up till 8 elements. Because if you are going to fill the 9th electron, then it will go to the 4th shell. And you know, if it is going to the 4th shell, then the highest principal quantum number is 4. That indicates that you are in the 4th period, which is not true. We are in the 3rd period right now. So as a result, we say that your 3rd period also contains 8 elements, similar to the second one. And what are the subshells that are present there? 3s and 3p. In that, 4 orbitals are present, which is 3s orbital, 3px, 3py and 3pz. That totals to 8 electrons and hence 8 elements. Now we can again look at their electronic configuration. If you compare the electronic configuration of second and third, then they are also similar. There is only a small change, that your outermost shell is the third one in case of third period, whereas it was second one in case of second period. So you just have to change it to 3s1, 3s2. So again, if I ask you, what is the alkali metal and alkaline earth metal and noble gas and your halogen in this table, what will be your answer? You will simply look at the last electron, right? So what will be the answer? Which is the alkali metal, which is the alkaline earth metal, which is the noble gas, and which is the halogen? So your sodium is the alkali earth metal, yes, and magnesium is the alkaline earth metal. So I am telling this again and again because when it is used in your language, it makes difficult for you to understand the textbooks. Similarly, your chlorine is the halogen and argon is the noble gas. So the important point is that why it is written 3p orbitals. So we are telling that, okay, these are the 3p orbitals. We are not giving a proper name to it. It can be 3px, 3py or 3pz. Okay, yeah. So it would be more appropriate if you write in the answer sheet that you write 3p subshell. Yes, that is true. But since we are talking about the orbitals of 3p, I have written it as 3p orbitals. Is it? I think it is clear to you. Now why they are noble? Again, octet complete in case of argon. Chlorine has S2P5 and you can also tell it as NS2NP5. So this is very important to remember. To remember the notation, how do you represent it? Because both the S and P, that is S2 and P5, they both belong to the same shell. So you can write it as NS2NP5. Similarly, for magnesium, you can write it as NS2 and for sodium, NS1. Then this is about the third period. Now we will see a drastic change in the electronic configuration as we will move to the next period. So I will suggest you to please remember the exceptions in case of electronic configuration, now which you will see in the fourth period, which you have not seen up till the third period. So this is very important point to remember, that your third period has no anomaly. The electronic configuration is absolutely according to the above principle. There are no changes. There are no application of Hund's rule of maximum multiplicity, which tells that the half-filled subshell is more stable. But this will be seen in the upcoming periods. Okay. So let us move to the fourth one. The period number 4. If I talk about the period number 4, then you would see that the order of filling involves the 3D subshell also. And the reason is very obvious. It is due to the above principle. Okay, and it was not filled in the previous period because it has a higher energy as compared to the 4s. You can just simply calculate it, n plus L value, you will get your answer. Now, if this is true, then what are the number of elements which is possible in case of the fourth period? So 4s means 2 electrons. If I'm talking about the d subshell, then it has 5 orbitals, therefore 10 electrons, so total of 12. And then p subshell, which has 3p orbital, therefore 6 electrons. This total goes to 18 electrons in total. Now, what are the subshells which are filled in the fourth period? My question would be that you will say that 4s, 3d and 4p are filled in the fourth period, and that contributes total of how much electron? 18 electrons, and therefore there are 18 elements in the fourth period. Now a question for you: which period apart from the fourth period has also this same number of elements? Till that, I am moving on to the electronic configuration. Yes, the fifth period has the same number of elements which is in the fourth one. So this is your electronic configuration. Now you would notice a blue colored compound in this whole table, which is chromium. Now this electronic configuration is very important for your examination. Questions are asked from here in every exam, including the competitive exam or your board's exam. Now, what is the anomaly here? That is to be remembered. So chromium has an atomic number of 24. You first fill the 1s, then the 2s, 2p, 3s, 3p, 4s. As you come to the 4s, you would see that before filling it completely, that is before making it 4s2, we are moving on to the 3d. Why we are doing so? Because in that process, you are obtaining 2 unfilled and I would say half-filled subshells. Now, this explanation would not be enough for each and every element. So I am telling it very clearly that there will be elements whose electronic configuration can't be explained on the basis of this half-filled and full-filled thing. And be sure that question would not be asked regarding this also, that why this have a different configuration apart from the half-filled and full-filled case, because that is totally a case of mathematical calculation. So we will not get into it. We will only remember those anomaly which has an anomaly due to half-filled or full-filled orbital subshell case, or in case you remember the one which is not due to the half-filled and full-filled, do not go into the meaning behind it or the reason behind it. Just simply remember it that it is an anomaly. Okay, so this is the basic thing. So if you look at here, you would notice that what is the alkali and alkaline earth metal in this case? It's very simple to answer. So your potassium is the alkali earth metal because it has S1, whereas the calcium has S2 as the last valence configuration. Therefore, it is a alkaline earth metal. So this is, and moving on to the next one. Here you will not tell that your cobalt is a halogen. What did I say? For a halogen, the configuration should be like S2P5. Okay, or I would say NS2NP5. We will see how it is possible that it is not halogen, because in this the D is having 7 electrons, and I have said that it must be S2P5 and not D7. So you would get an idea when you will look at the real halogen of this period. Before that, you must see that how beautifully that electrons are filled. So first of all, the S is filled, then we move on to D, then we come across the exception of chromium, and lastly we move on to the nickel. Then what about the remaining elements? If you count it, they are not 18. So in this table, you will be able to see both the noble gas and the halogen of this period. So what is the halogen here? If I ask you what is the halogen, it is bromine. Yes. How do I saying this? Just look at the electronic configuration of bromine. If you see the last three terms, it is 4s2, 3d10, 4p5. Now you can see 4s2 and 4p5, which is representing the ns2 and np5. Got it? Therefore, we will call it as a halogen. So the idea is that the subshell which has the 5 electrons, which is the p subshell, should also have a corresponding s subshell, which should have a completely filled s orbital, which is 2. S subshell, which is 2. Similarly, if you look at the krypton, it has a ns2 np6. So here krypton is a what? Which type of element? It is a, so krypton is a noble gas, right? Okay, very good. Now let us look at the anomaly. So if I ask you what is the anomaly here, it is being underlined and it's very clear. So the anomaly in this case would be your copper. So anomaly means which is an exception part. Now there is a small problem in the configuration. It should be 3d10, right? So don't worry, it is 3d10 at the last. Now again, why are we doing it? Why are we telling it an exception? Because if you look at the electronic configuration, you will see that before completely filling the 4s, we are moving on to the 3d. We are moving because your 3d has a full-filled subshell in this case. Therefore, it is an exception. So two exceptions we have seen in the fourth period. Remember those names, chromium and copper. Chromium is due to the half-filled d orbital and copper is due to the full-filled d orbital. I guess this is very clear to you about the electronic configuration of the fourth one. And hence now we'll move to the fifth one. Now if you look at the rest of the electronic configuration before moving on to the fifth one, you will notice that there is a clear and crisp increase in your electron number without any anomaly. There is a 3d10 and next we have 4p, 1, 2, 3, 4, 5 and 6. What about the fifth period? How many elements are there in the fifth period? So there are total of 18 elements in the fifth period. Now again, why it has the same number? Because we cannot fill the 5d and 5f right now. So you have the 5d, you have the 5f. But before that, 6s is having a lower energy. And as a result, you have to stop at the 5p only for the fifth period. I am again repeating it. So this is very important to remember. Which are the orbital subshells which are filled in the fifth period, which is 5s, 4d and 5p. The reason behind it is that if you fill the next corresponding subshell, then it would be 6s, which has a lower energy than the 5d. Calculate the value of n plus l for 5d. 5 plus 2, for d it is 2, so 5 plus 2. For the case of 6s, the total energy will be 6 plus 0. So the n plus l value is 0 for 6s and for 5d it is 7. And hence your 6s is a lower energy. Therefore, it will be filled first. But you can't fill it in the fifth period because the fifth period can only have those shell filled where the value of n is 5 or less than 5. I guess this point is clear to you. Now let us look at the electronic configuration. So the electronic configuration of the fifth period has a lot of anomaly or exceptions. And as I have added it first, that you can't explain all of these exceptions. It is not possible. Okay. You can explain it for the molybdenum, but you can't explain it for the niobium, as The 4d4 is not the case of half-filled orbital. So this is very difficult to explain. Now you will notice one very important point here, that we are not seeing exceptions up till the third period. We are seeing in the fourth period only. What is the reason behind it? Why it is not possible for the previous cases? So if you have any guesses, you can think of it. What is the reason that you are only seeing the exception in electronic configuration starting for the fourth period and not for the third one? Now this is very interesting to think of. The reason is the involvement of d orbital. As you move on to the fourth one, you are now dealing with the d orbital, because there is an entry of 3d which was not filled in the previous period because it would change the above principle, but now it has to be filled in the fourth period. Now this d subshell is very I would say complex to handle. Okay, so this is the reason behind it. Remember it, because of the involvement of d orbital, we see exceptions in the electronic configuration, right? So if you look at the exceptions here, then the important exceptions would be molybdenum and palladium. Although you have exceptions apart from it, like for the niobium, ruthenium and rhodium, which has filled the 4d before completely filling the 5s, because they have one electron in the 5s. Now there is a very complex reason behind it. I will not go onto that, but at least you should try to remember those exceptions which are explainable, right? Like your molybdenum and palladium. And if it is possible, try to remember each of this exception. Now, these exceptions should only be remembered to fifth period, because that is significant to you. After fifth period, you do not need to remember the electronic configuration. Okay, in case of exception, right? If it is an exception, leave it. But up till fifth period, you should remember it. That is very, very important. So as I told you, your molybdenum and your palladium, they both are stable due to the completely filled d orbital in case of palladium and half filled d orbital in case of molybdenum, and rest of the electronic configuration have a general trend, no anomaly. You simply fill the upcoming subshells according to the above principle. Now, what are the alkaline and alkali earth metal in case of fifth period? So what are the names of it? So we have seen right now. What are the names of your alkali and alkaline earth metal in case of fifth period? So it is rubidium, right? And strontium is your alkaline earth metal. Very good. Now, the one exception that is being seen here is your silver. So silver also has a exception in the configuration. You can look at it, and it has also a completely filled d orbital. Rest of the elements have a normal configuration. So if you look at the table, they are filled in a very normal order according to the above principle. Then moving on to the next period, which is period number 6. Okay, now if I ask you what are the halogens here and what is the noble gas which is present, so it's very easy to guess. So what are the halogens that we have seen till now, starting from the fluorine? So we have seen the fluorine, then comes your chlorine, and after that we have the bromine, and lastly we will see the iodine. Now you have you don't have to worry about the halogens after this metal, after this period. Now one more question. What are the noble gases that we have seen till now? So I'm just trying to make you revise all of this. What are the noble gases that we have seen till now? It is neon, argon, xenon, right? So moving on to the sixth period. So if I talk about the sixth period, there is a slight change in the sixth period. First of all, remember that your sixth period is the longest one. So there are two periods which are the longest one. They both are in the count, which is the sixth and the seventh. They both have 32 elements, right? And as a result, they are the longest period. So what is the order of filling here? First we fill the 6s, then we fill the 4f, then we fill the 5d, and then we fill the 6p. Now if you look at the periodic table, then you will see that whenever you fill the 4f subshell, you don't keep that elements in the same period. Okay, means in the same line. Of course they will remain in the same period, which is the sixth period, but we don't place it there. Rather than we place it in the bottom. So for the noble gas configuration, it must have a NS2 NP6 type, right? Not D10. So D10 is not your noble gas configuration. It is your NS2 NP6. So 6 electrons in the P, and in that same shell 2 electron in the S. So that's it's the basic idea for the noble gas. Okay. Now why are we placing this lanthanide series in the bottom and the actinide series in the bottom? We will see the actinide also, because if you look at the whole table, we will discuss about in the next class about the different blocks. For the first two blocks are S, then we have the D, then we have the P, and so on. So that configuration is not fitting if you are putting this 4F in the same line, because the F series element or the F block elements are placed in the bottom. Okay, for keeping them apart in the separate block, which is the F block, we don't keep in the same period, in the same line, because in that line we have D block. So we will see on to it when we move on to this block part. You will notice that. Now remember a very important point in this, that in case of lanthanoid, your 4f orbitals are filled, right? And we start from the cerium and we move out to lutetium, which is 71 and 58. So this atomic numbers are also important, 58 to 71. So after 57 you will see the 72 in the case of sixth period, right? And you will notice them written in the bottom. Now they are also called as the inner transition series, right? They are also called as the inner transition series. So first of all we fill the 6s, then we keep the 4f1 in the down. After that we fill the 5d and the 6p. So that gives you your total period elements. Now we should not be interested in the electronic configuration of the elements of the 6 periods, because they are not asked in the exam, in any of the exam. Until and unless those configuration is given, you will not be asked questions related to its configuration, right? So you shouldn't be worried about the 6th period and the 7th period, but you should remember that after which element you see them in the bottom panel. So from the cerium to the lutetium, which is atomic number 58 to 71. Okay. Now moving on to the 7th period. So again, the 7th period is also the longest one out of the two. 6th and 7th, they both have 32 elements. So they are the longest one. Now why it has 32 elements? Because this is the order of filling. So this order of filling is also very important. Remember this: 7s, 5f, 6d, 7p. If you subtract 1 from each of this, you will get it for the previous period, which is 6s, 4f, 5d, and 6p. As simple as that. Now, firstly, your 7s will be filled. So that will contain 2 electrons. 5f will contain 14. So 14 plus 2, 16. 16 plus 10 of d, 26, and 26 plus 6, that is 32 elements. So just count the number of electrons possible for these 4 subshells and you will get your number of electrons. I guess this is clear to you. Now, again, similar to the 7th period, you will also see a change in the element as soon as you cross the atomic number 89. After 89, you will see the 90th element placed in the bottommost series, bottommost line. But remember student, they will belong to the 7th period. Although they are placed in the bottom panel, they are in the 7th period. Okay. So from starting from thorium, moving on to lawrencium, which is atomic number 103. Then after filling the 5f orbital, which are also called the inner transition elements. So 4f, whenever the 4f is filled or the 5f is filled, those elements are termed as the inner transition elements. And for 4f, it is lanthanoids, and for 5f, it is actinoids. So your 5f orbital enters the 6d, and finally the 7p orbital is filled. So again, you don't have to worry about the electronic configuration in this case. So the thing is that, why are we not writing the lawrencium as unyl trium? So if you remember my previous class, you must have seen that I have written a point that this IUPAC name is not given to the element until and unless its discoverer is finalized. If it is proved that yes, this person has discovered the element, then the IUPAC name is removed and the name which discoverer suggests is given to that element. Okay, so that name is a temporary one. So the part you get the element, you name it as according to the IUPAC. Now IUPAC decides that who has discovered this, and the discoverer decides that what will be the name of the element, and hence its name is lawrencium. Okay. So I guess this point is clear. Now moving on to the next one. So why are we putting this inner transition series as are shown in the separately? So why are they shown separately? So this is a very, very important question. Question can be asked in your board exams in the same pattern. So what you would write? You will write that they are placed in a separate row in the bottom panel. Why? Because in their filling, we fill the F subshell, and the column which is provided there is the D subshell. So to make the difference clear between the D and F, we place them in the bottom. Now the question arises, what are those lanthanides? Although you don't remember that what are the elements of the all of the periods, that is 5th and 6th, but you should remember the lanthanides of the 5th period and the 6th period. So that is important, right? So the names of the lanthanoids are very important for you. Now you can devise your own mnemonic for it. So mnemonics means like a song or a code word to remember all of this, but you have to remember the lanthanoids. And when we will move on to the DNF block in your class 12, you will see it. You should also remember the electronic configuration. So I would suggest you that you don't face difficulty in that part. You must write the electronic configuration also. You can refer the book for it, the 12th class book, and try to remember it. So it's not very difficult. Okay, once you get it, it will be helpful for you in your competitive exams, especially for your competitive exams. You will surely obtain marks if you remember the lanthanide names and the electronic configurations. There is a maximum chance of it. So similarly, we have the actinoids. So these are the names of actinoids. So I'm just giving you the table Now it's your duty to remember all of this. So again, I'm making you remember that. Why are they shown separately? Because in that filling of electrons, the f orbital is filled, and the block which is there, which is the d block, so we place it in the bottom size for a separate place for the f block. Then here is a question from you from the NCERT, problem 3.2. How would you justify the presence of 18 elements in the fifth orbital of the periodic table? Now we have already seen it. Why is it so? So I am giving you some time to write an answer. The time starts now. Okay, your time is up, because the total number of orbitals are 9. Yes, what is the answer? That the total number of orbitals are 9. So if you look at the fifth period, then you will see that n is equals to 5. So L values possible are 0, 1 and 2 and 3. So the order would be, for the valence one will be 4d, 5s and 5p. So this is the order: 5s, 4d and 5p. Therefore, the total number of orbitals which are possible are 9, and hence you can accommodate only 18 elements in this, because 18 electrons are possible. We have already seen this justification in a very broad explanation way. Okay, I guess this point is clear to you. Now, moving on to the next question. Which of the following is not an actinoid? Now, this may be a problem to you if you are not aware about the names, but still, if you are accessing your book or something, then you can look for the answer. There is no problem, but I will suggest you to learn the name as soon as possible. So your time starts now. The correct answer will be terbium, which is having an atomic number of 65. So if you look at the table which represent the actinoids, then they are actinium, thorium, proactinium, uranium. So you have the uranium, neptunium, plutonium, americium, then you have the curium, right? Then berkelium, californium, einsteinium, and lastly fermium, nobelium, lawrencium and mendelevium. So you won't see the terbium in this whole table. Then the next question, the elements in which the electrons are progressively filled in the 4f orbitals are called. So we have already discussed about it. It's an easy one. Your time starts now. So what will be the correct answer? The elements which are filled in the 4f orbitals are called as lanthanoids. Now what about the 5f orbital? So for 4f it is lanthanoid, then for 5f it is actinoids, or you can write it as actinides also. There is no problem in that. So I would give you some key points that is related to this whole discussion of today. What are those key points? The first one is, the number of elements which is allowed is equals to the number of atomic orbitals that are filled. Twice the number of atomic orbitals that are filled. The first very important point, we have seen it clearly. Now there is a case, you have the above principle and all. You should remember that. The second point, you will see an electronic configuration anomaly from the fourth period only. Before that, you don't have to think about the anomaly. Simply take, if it is from the third period, simply take the above principle, start filling the electron, you will get your electronic configuration. After that, you have to think of it. And I should say you remember the names. It is very, very important. Now, what about the lanthanoids and actinoids? So they are placed in a separate panel. We have talked about it. And the reason behind it is that because in that case your F subshell is filled and you should place F subshell in a F block that involves the filling of 4F and 5F, that is for lanthanoids and actinoids. So this was all for the theory class, right?